This is the 11th lecture of the course MTH 204A for section B. Recall that in the last lecture we were talking about orbits and stabilizers in the actions of general linear groups. So let as usual F be as usual, A, Q or C, and V be a vector space over F. Then the general linear group of V acts on V. So in the last lecture we discussed the orbits and stabilizers under the action of the general linear group and its important subgroups. So now we are going to consider the following special case. So let V be F2. So thus then GLV is nothing but GL2 of F. So for now let's denote by G. So either GL2 or SL2. And we consider the action of G on F2. So let's take the vector E1, 1, 0. So what is the stabilizer of this vector E1? It's easy to see that the stabilizer is precisely the following subgroup of G that consists of all matrices of this form, right. This is the stabilizer of the vector E1 in G. When G is SL2, then even in this position we must have 1. Okay, so let me define B to be this subgroup upper triangular invertible matrices. If if G is GL2 or when G is SL2, let me rather put a further condition. AB 0D, AD equal to 1. So just to make this the subgroup of the G, if G is SL2, okay, G is SL2, and it's easy to see that this stabilizer is contained inside B. So for both G equal to GL2 or SL2, GL2 and SL2, in either case the stabilizer is easily seen to be contained inside B. Okay. Now let's look at the orbit of E1. So since the action of G on F2 is transitive, therefore the orbit is the orbit of E1 is the entire F2. Now let's observe the following, that okay, maybe we can put this in this way. So let B be in small b in capital B. So therefore B, we look at BE1. So B is either of this form or of that form. However, we see that BE1 is a vector of this form, right. So we can see that BE1, so the orbit of E1 under the action of this subgroup is nothing but the all points is nothing but the linear span of E1, right. So I should put that in this way, that all points, maybe I can directly write this, that's better, linear span of E1. Okay. Now in order to see whether we can have some sort of similar description for the points which have, say, a non-zero second component, let's observe that if we consider this matrix 0, -1, 1, 0, so the WE1 is nothing but 0, -1. So therefore it follows that. So for a typical, let me put it in this way. So for a typical, if B in B, then BWE1 is of course of this form, that 0, okay, yeah. So because this is of this form, and just a minute, yeah, so a typical B will be of this form, yes. So however, one thing is to be clear, that this component cannot be 0, so the second one has to be non-zero. Okay. Let me put it in much more concrete way, that my claim is, so from this observation my claim is BE1 is the set of all x comma y in F2 such that y not equal to 0. Why so? That is very easy to see. So take we have already observed that this has already second component non-zero, because that comes from the, that actually comes from the second row of, so again let me do it for you. So if well, I should be somewhat careful while choosing the notation. So if A B 0 D W E1, that means A B 0 D 0 minus 1, so thus you get minus of B comma minus of B comma D, right. So that immediate, so since D is non-zero, so any point in this orbit, any point under the orbit of B okay, so under the action of B, the orbit of WE1 must have, so in every point in the orbit must have the second component non-zero. That's all we have seen. And to see the other direction, so if x and y are two such vectors with a y not equal to 0, what we have to do is, we have to do this, we consider this matrix, then minus 1 by y, 0. So this is certainly inside B, and what we have observed this is nothing but x, y. So thus this is now quite, this is now clear to us. Hence we see that we got the following decomposition of F2. So what is the decomposition? In one hand I have all the points which are having 0, first component 0, and together with that, so this is basically, as we have already seen, BE1, and here we got BWE1. So that's how, so this is the orbit decomposition of the action of this subgroup B on F2. Now the reason for considering this, so starting with the action of G, the reason for restricting our attention to the action of this and looking at its orbit is the following, that from this decomposition, that is the orbit decomposition of the action of this subgroup, we will get a decomposition of the group G in the following way. So claim is G is nothing but B disjoint union. So this stands for the disjoint union, that is set theoretic union. It is put just to remind you that, just to tell you that the intersection is empty. So B W B. So this is nothing but the collection of all elements of this form, B1, B2. So I had B1 and B2. These are matrices lying inside B. So this is the claim. Why this is true? So let G be from G. So certainly, so then we look at GE1. GE1 is in F2. So either GE1 belongs to here or belongs to there. So in the first case, if GE1 is of this form, then that means B inverse G E1 is E1, that is B inverse G stabilizes E1. Now we have seen that the stabilizer is contained inside B. So therefore B inverse G is in B, that forces G to be in B. So this is one situation. If GE1 rather lies in this part, so if GE1 is of this form, that some BWE1, then that's also quite obvious that W inverse B inverse G stabilizes E1, hence it will be inside B. That implies G will be yes G will be BW, G will be inside BWB, right, because first multiplied by W then by again B, yeah. So this is inside B. So thus it is clear that G is the union of these two sets. So remember, this is a subgroup, certainly this cannot be a subgroup because the union is disjoint. Yeah, well, I haven't settled that union is disjoint, so let's wait for a while. Yeah. So I have just showed that it is just the union. I will now show that the union is in fact disjoint. That's also quite easy to see, because if there is something in common, then the situation would be like this: some B equal to B prime W, B equal to some B1 W B2. So that's essentially same as saying if you pull this inside, so the situation is same, this some B prime equal to W B2, where B prime is B1 inverse B. Now if this is the case, if these two elements equal, then one must have E1, right? But now you see that this has second component 0, which you have already observed. However, this cannot have second component 0, because again, so like if the second column of B2 is so what do we have? So this just nothing but gives us the first column of B2, which is necessarily of this form, right? And then once we apply this, then we will get so this cannot be 0, so therefore this has second component non-zero, which, as I said, which I have already seen. So thus this cannot happen, hence it now it is established that this union is disjoint union. Okay. So in view of this disjoint, thus from the decomposition, orbit decomposition of this B, orbit decomposition under the action of B, one obtains a decomposition of the group G. This decomposition is actually very important. We will use that later on many times. We call it the Bruhat decomposition of G, where G is GL2 or SL2. So let me write it. The Bruhat decomposition for G. I will show an immediate corollary for that. Bruhat decomposition of GL2 or of G, where G is either GL2 and SL2. Okay. So this W is same for both of them. However, the B for GL2, B is for GL2 and SL2, the B will differ. Okay. But however, whatever be that subgroup B is, this always holds. Let me draw an immediate corollary for that. Let me draw an immediate corollary for that. So the corollary, B is a maximal proper subgroup B is a maximal proper subgroup of G. Again, G can be as GL2 and SL2. So why so? That's quite clear that if an element does not belong to B, then it must belong to this. So the proof will go in this way, that if there is a subgroup containing B strictly, then N must contain an element of this form, some B1 W B2, it must contain an element of this form. Okay. Now it implies that since N contains B, so every B prime contain N for every B prime and B double prime belonging to B. because this is in n and these elements are also in n. Now when b1 and b2 are fixed, multiplying by arbitrary b prime and b double prime, we in fact get all. Now n already contains b and n all contains this, so from this decomposition it is clear that n equal to g. So thus from this decomposition, as a corollary, it follows that B is a maximal proper subgroup of G. Okay, so now we will move on to some other actions. So the actions of GLN on its on GLN or actions of GLN or its important subgroups on the vector spaces. We have for such actions we have talked about several examples. Now we look at some other examples of GL and G of this general linear groups. So okay, so let me read in this way that let V be a vector space over R. Whenever necessary, we will assume this way finite dimensional. Vector space over F, and let R be a positive integer. We consider the set of all R dimensional subspaces of V, and it's quite clear that GLV acts on that in the most natural way. So A and W, it goes to AW. So what about this action? What are the orbits under this action? So if we take any two R dimensional subspaces, then we can. So we first fix a basis, an ordered basis of W and another ordered basis of W prime. Then we can. So if W1 up to WR is an ordered basis of W and W1 prime up to WR prime is an ordered basis of W prime, then we can construct an invertible linear map which sends each Wi to Wi prime. These things we have seen already, so therefore this action is transitive. Okay. Well, when V is finite dimensional, this is quite easy to see. For V infinite dimensional, like what's the main point? Point is that every linearly independent set can be extended to a basis of the vector space. For finite dimensional, that's easy to see. For infinite dimensional, you just have to do some work, that is you have to pass through quotients. But and you have to the main fact is you have to use that every vector space admits a basis, which is a usual application of John's lemma. Okay, so in either case, so whatever be the whether V, irrespective of whether V is finite dimensional or infinite dimensional, we can see that there is an invertible linear map that sends W to W prime. So therefore this action is actually transitive. And in the special case when the dimension is finite and at least 2, then it makes sense to talk about the action of SLV, the action of SLV on V, sorry, not on V, this the collection of subspaces, and this action is also transitive because if like yeah, so how to see that action is transitive? That's actually easy. So first you fix some well, so if W and W prime, these are there. So what we do is the typical argument W1 up to WR, we fix an ordered basis of W and another ordered basis of W1 up to WR prime. Now there will be a invertible linear map sending each of them to. Okay, let me do this in this way. So that's actually quite clear. So let me again repeat the argument for you. This ordered basis, you just extend that to an ordered basis of V, U1 up to R, let's say K. Let's call it B, and then we can construct a linear map sending each wi to wi prime. So therefore, it's easy to see that A sends w to w prime. However, there is a slight controversy that whether this A is allowed to, this A is having determinant 1 or not. In that case, like earlier, we may simply scale some column appropriately, and by scaling the column. So again, let me repeat for you. So what I mean by this is we look at this matrix. Let's call it determinant. Determinant is D. If D is not 1, then like earlier we will scale some column by this scalar D in order to form a new matrix having determinant 1. And since we have just scaled, that means so the image of their span will go to the image of their span. So image of the span, so the image of the span of this will be the span of these vectors. So my suggestion is that you may first do this concrete case, then you will understand. So in Fn, so consider this subspace, let's say this following subspace x1 up to xr, the rest are 0. Okay, xi is in F. So this is an R dimensional subspace. So it is spanned by E1 to ER, right? You extend this basis as earlier to up to En. Okay. Now let the basis of the other subspace is, let this be W1 up to Wn. So you can consider now an invertible matrix whose first R columns will be W1 up to Wr, and then will be something which I don't care. Now you just scale any of the first R columns if necessary to make the matrix of determinant 1. The same thing is the same observation, the same strategy is carried out even for a general finite dimensional vector space, and that has to be because any two finite dimensional vector spaces like any finite dimensional vector space is isomorphic to some Fn. Okay, so thus the action of SLV is also transitive. Okay, at least in this case it's interesting to compute the stabilizers. To see a concrete description for that, let me consider this concrete case only. So since the action is transitive, so all the stabilizers will be basically a conjugate of the stabilizers or conjugate of the stabilizer of this subspace. So what's the stabilizer of this subspace? So the stabilizer of this subspace, so E1, so AE1 must be a combination of E1 up to ER, right? So this components of the last n minus r vector has to be 0. Similarly for E2. So that shows that the matrices which stabilizes this subspace is of this form. So something will be here. The main point is this block has to be 0. The size of n minus r and r, this block has to be 0, and anything else could be here, I don't care. So all the matrices, invertible matrices of this form will be the stabilizer of this, and for the stabilizer of the Slnf, we just have to add the further condition that those matrices will have determinant 1. Okay. So the action of GL general linear group and special linear group is already covered. Now I think it's better idea to go for the orthogonal groups. Okay. So now onwards, let's assume that V is a finite dimensional inner product space. So B is finite dimensional inner product space. Inner product space over R or C, so complex or real inner product space. And in that case, let OV is nothing but the group of all orthogonal transformations of V, and if V is over R, otherwise we consider all the unitary transformations of V, if V is inner product space over C, and certainly we do have the action of, in either case, the action of this, where 1 less or equal to R less than dimension V. Okay. And so in this case, what about the action, what about these actions, what about the orbits under these actions? Let's do one of them, the other one will be easier. So if we take this one, so like if we take any two subspaces W and W prime, since we are lying in a finite dimensional inner product space, we can take we can choose orthonormal basis of both these subspaces. So which is an orthonormal basis of W and another orthonormal basis of W prime, extend them to an orthonormal basis of V, which we can do by means of using Gram-Schmidt if necessary. Then we do have, so if W1 up to WR is an orthonormal basis of V, we extend that to an orthonormal basis of W, then we can extend that to an orthonormal basis of V. Similarly for the another orthonormal basis of W. Now, so well, let me put it in this way, we extend that, and similarly okay. Now we know what to do. We take a linear map that maps each Wi. So each of these bases, so here ith basis vector to the corresponding ith basis vector of the ith basis vector of the former, it takes the ith basis vector to the latter. Since the bases are orthonormal bases, that transformation is certainly going to be an orthogonal transformation. So thus this shows that this action is transitive. Similarly, the second one also. So let me write just saying that these actions are transitive. Let me just write it somewhere. Here also we should look at the stabilizer. So here let's say again, to see the stabilizer concretely, we will take the concrete vector space Fn. Sorry, let's maybe in case of let's take Rn. Similarly, we can do it for Cn. Then the matrices stabilizing the standard subspace generated by E1 into ER. So E1 into ER is linear span. So what will you get there? Of course, here we should have 0 and here. So this here we will have something. Let's see what it is, what we can say about that. However, we can say on this that these columns, they will be, so each of the first R columns will have unit norm and inner product of any two will be 0, right. So from that it follows that this A must come from again the orthonormal group of R, and again so if we take any column here and if we take any other column here, the inner product will be 0. So this forces that even in this block we are supposed to get 0, right. Even in this block we are supposed to get 0. So and as usual here we will have B, so this also has to have from On. So therefore we see that the stabilizer of the standard subspace is actually isomorphic to, stabilizer is isomorphic to ONR, sorry OR Cartesian product On minus R. Okay. Thus what we can see that by this orbit stabilizer theorem we can identify this space in this situation with this quotient OR On minus R. So one word of caution is whenever I am, so technically speaking this is not set theoretically contained inside ONR. What I mean by this is contained in this manner. That is, an element from this Cartesian product corresponding to each element from this Cartesian product, we will identify that with the corresponding block matrix, and that is going to be contained inside ONR. Alright, and once you have something from ONR, then it's again natural to ask what you can do for SONR, and similarly here. So okay, so let me rather leave it as an exercise. So what happens to the action of SONR on GRV? This is actually not at all any big deal, and similarly we can of course go for so the real case I have just done. So the complex cases also can be done in the similar manner. So I would like to leave that as an exercise. So UN is isomorphic to, so when V is over C, then this space GRV can be identified with UR cross UN minus R. So there is a bijection from this GRV, and similarly we can ask what happens to the action of SUN or this. Okay, is this transitive or whatever? So the similar question where the questions that we have dealt with for this real case, the same questions we can put for the complex ones as well. Okay, so the enough actions of the GLV and SLV or in the inner space of inner products with orthogonal, this orthogonal or unitary group on this collection of subspaces we have discussed. We have seen that they are transitive, and they are stabilizers in some cases do have a very concrete and interesting description. Now we move on to some other actions of the linear groups. So now the actions that we are going to consider are the actions on the flags of subspaces. So as let me do it in this way, that so as usual V be a finite dimensional vector space over F. Remember that by a flag we mean a chain of subspaces of this form. So let us call it V0, V1 up to Vk, V1 up to Vk. So in order to avoid any unwanted, like in order to make things nice, we assume that all these containments are proper. So we say that this is a flag of length k. So all Vi is a subspace of V is a flag of length k, and if this is n, then flag of length k is called a maximal flag. We have already seen that every flag can be extended to some maximal flag. It can be refined to some maximal flag. Now the group GLV and of course SLV acts on this collection of all flags. So fix any k, collection of all flags of length k, right? Because once you apply a linear operator, then the containment is going to be preserved and the dimension will also be preserved, because you are dealing with invertible linear maps. Therefore, yes. So given to now we will also see that this action is transitive. So given to maximal flag, given to maximal flags, let us say V1, V2, Vk equal to V, not maximal, given to flags with the same length k. Similarly here also, if we have analog 1, V prime 0, which is trivial, what we can do is we first start with a basis of V1, then extend that to a basis of V2 and keep on extending that, I can get a basis of V. The similar thing I can do here as well. So now I have two bases. If we map each of the bases, the ith basis vector to the corresponding ith basis vector of one to the ith basis vector of the other, then we get a linear map which immediately shows which is evidently sending each Vi to Vi prime. Okay. So thus we see that here also the action is transitive, and the action of GLV, and for SLV the idea is similar. We just have to scale it appropriately, then we get the operator of determinant to 1. So both these actions are transitive, and in this case let us look at the stabilizers, because whenever we have a transitive action, at least it is enough to find the stabilizer of any one of them. We sometimes try to choose the one which gives us a much more concrete description. So like if we start from here, let us say V1, V2, V1, N1. So okay, let me put it in this way. So suppose we start with a basis here. So let V11 up to V11 up to, yes, I think that's it's better that V1 up to R1, let this be a basis of V1. Then we further V1 up to VR1, okay. So VR1 plus 1, we extend that to a basis of V2, let's up to VR2, and if we go on like this, we get an ordered basis for V. Let's denote this basis by B, and with respect to B, if we look at the, so let A stabilizes this flag. Let A stabilizes this flag. Then what is going to be the matrix of A with respect to this B? That's quite easy to see, because so how will the matrix look like? It will be block upper triangular form, right? So for the first there will be an so it will be block upper triangular form. So what I mean is, first there will be an R1 block, so elsewhere everything will be 0, because the image of this V1, V2, VR1 will be a combination of themselves. Then we have a bigger block, so this has size R2, so there is up to R2. Then we have perhaps a bigger block, so that's how it will keep on going. Okay, so this is somewhat you can think there is a generalization of upper triangular matrices. So here you are rather having block upper triangular matrices, that is above the diagonal you have blocks. Okay, so in particular when this K is n, that is a maximal flag. For a maximal flag, each of this, like for a maximal flag, R1 will be 1, R2 will be 2. So in that case, what you will get is an upper triangular matrix, right? Okay, so let me, okay, fine. So the stabilizer will be precisely all upper triangular matrices. So let me put it in this way, that let me make a definition here. In any finite dimensional vector space V, in any finite dimensional vector space V, just let's do the following, that finite dimensional vector space V, the stabilizer, okay, fine, definition, a parabolic subgroup, let me parabolic subgroup of GLV, parabolic subgroup is the stabilizer of some flag. In V. So let me elaborate that, what I mean. So by a parabolic subgroup of this general linear group, I mean the stabilizer of some flag, okay, of some flag. So example, when V is Fn, so what are the examples of parabolic subgroups? So the all matrices. So parabolic subgroup of GLV, okay, fine, let's do it for GLV. So by a parabolic, so let me give you an example. Let's say let this be a 2 by 2 block, 1 2 1 2 5 6. Well, and then let's have another block, all matrices of this form. Yeah, let me put it in this way. So let's fix some we can make, let's leave it, let it, this has 2, this is also 2 2. So this is a so all matrices of this form is a parabolic subgroup of GL6F, okay. And in the special case when it's a maximal flag, then we call it a Borel subgroup. So a Borel subgroup of GLV is the stabilizer of some maximal flag. Okay. So for example, let's say example of a Borel subgroup. In case of Fn, this is just the upper triangular matrices. Okay, and in fact, you can see that that any parabolic subgroup of GL and F is conjugate to some subgroup of this form, and similarly any Borel subgroup of GL and F is conjugate to this standard Borel subgroup, which consists of all invertible upper triangular matrices, okay. Because inside Fn we do have a for given any length, we do have a standard choice of a flag of length the same L, and if you look at its stabilizer, it will be of this form. So here, for example, let's say for this case, so we have trivial subspace, then the linear span of E1 E2, E1, E2, then E1, E2, E3, E4, then finally F6. Okay. So, the collect all matrices of this form, this is the stabilizer of this standard flag. So, therefore, if we take any flag with length 3 and having each of the subspaces dimension, this dimensions 2, 4 and 6, then its stabilizer is going to be a conjugate of this, right. This is because of considering different bases is same as considering conjugate of the matrices. So, thus parabolic Borel subgroups in GL and F are the conjugates of the standard Borel subgroup of invertible upper triangular matrices, and in a parabolic subgroup of GL and F is conjugate to some subgroup of this form. Okay. So, similarly we can talk about parabolic subgroups of SL and F and Borel subgroups of SL and F. Now, you can remember that in the first example that we have started with, we use the notation B. So, in case of F2, what was our collection? A, B, 0, B, D, right? So, that's nothing but the standard Borel subgroup in GL2, and similarly when we further add this condition that AD equal to 1, then we get the standard Borel subgroup in SL to F. Yeah. So, thus the general concept is parabolic subgroup. Parabolic subgroups are stabilizers of some flags, and Borel subgroups are stabilizers of maximal flags. And you see that any two Borel subgroup must be conjugate to each other. However, this may not be same for parabolic subgroups. Of course, it will not be. But however, if two flags are given where here I should have put one more condition that I should have said that each dimension V is a dimension of V prime. If two such flags are given, then the parabolic subgroup corresponding to this and the parabolic subgroup corresponding to coming from this, they must be conjugate to each other. That is what we can say in general. All right. So, let me see whether I have anything else to say about the actions of linear groups. Maybe not. I can just say one or two small things and simply go ahead. So, now let us be concrete. GLNF, MF acts on M n cross n F, right? How? So, basically if I map P A, this goes to P A, okay, the usual matrix multiplication. So, here what are the orbits? So, given an A, what is its orbit? Its orbits consist of all matrices which are row equivalent to A. Okay. Similarly, we can consider the action of GL and F on Mn cross Nf. How? Basically, Q comma A maps to A Q inverse. So, here also given a its orbit consists of all matrices which are column equivalent to A, and if you want to combine them together, so here it's easy to see that for any A, what's the stabilizer. So, yeah, maybe I can leave all this to you, that yeah, maybe they come, since I don't have much time, maybe I can leave the job of finding the stabilizers in these two actions, and I will simply move ahead for their combination. So, what we do is we basically take combine these two actions on the same set in the most natural way. Yeah. So the action would be in this way, that P and Q and the A, it goes to P A Q inverse. Okay. I leave this to you to check that this indeed defines an action. And then what about the orbits under this action? It's a simple exercise in linear algebra that it has like so like minimum of, if we call this minimum of Mn, so it has exactly these many orbits. In fact, we can prove that each orbit contains a matrix, a unique matrix of this form. These are easy exercises in linear algebra. Each orbit contains a unique matrix of this form, and from that it follows that we do have only these many orbits. Okay. And just to see a stabilizer, if we take m equal to n and a to be identity. So in general, here the stabilizers are not so good looking, but yeah. So let's then take the special case, then m equal to n, and let when m equal to n, and let's take a equal to identity. Then P identity Q inverse is identity. It implies that P is equals to Q. So P is from so therefore, thus we see that under this action the stabilizer of identity is precisely this one, right. So basically we are considering the diagonal embedding of GLNF inside the GLNF plus GLNF. So diagonal embedding means each P is being embedded in as PP. Okay. So here in this special case, the stabilizer is we have a nice description for that, but in general that's not the case. Okay, so enough examples of orbits and stabilizers under linear actions we have discussed. Now we should move for other actions of other groups. Yeah, I think I haven't missed anything. So this Borel and parabolic and Borel subgroups we have done. Again, let me remind you that parabolic subgroup means it stabilizes some flag, and any two flags of same length and with all the subsets of the same dimension, their corresponding parabolic subgroups will be conjugate to each other, and maximal flags stabilizers are the Borel subgroups. So any two Borel subgroups in GLV are conjugate to each other. All the similar things also holds for SLV. So all the necessary small details I am leaving to you. Now let me move towards actions of any group on itself. So for any group G acts on G. There are three ways for that. First one is, let's consider the case for left multiplication. So it's easily seen to be transitive. In fact, we have already seen, and the stabilizer of any point is easily seen to be trivial. Now what we can do is we can restrict, we can take H some subgroup of G and consider the action of H on G. So in this case the orbits are nothing but, you can see, the right cosets. Okay. Similarly, if we take the multiplication from the right instead of left, the orbits would be the left cosets, and the stabilizer is also quite easy to see that the stabilizers are also trivial, because some H into A is A means H has to be identity. So stabilizers are here also trivial. Now let's go for the actions on the cosets. So let Hk be subgroups of G. Consider the set of all left cosets of K in G, and of course G acts on that, but we restrict that action to H. Okay. So in this action, what are the orbits? So given a coset AK, its orbits are precisely of this form, right? So basically this is nothing but H AK. These objects are called double cosets. So in this action, the orbits are the double cosets. And what about the stabilizers? What about the stabilizers? The stabilizers is simply H AK is AK, that implies A inverse HA belonging to K, or equivalently H belongs to A K A inverse. Thus it says that the stabilizer is in fact A K A inverse intersection H. Okay. So given A, this is a stabilizer. In particular, when A is identity, the stabilizer is K intersection H, and in that case by orbit stabilizer theorem, when G is finite, this is exactly number of distinct orbits, number of distinct cosets of the form distinct cosets of K by elements from H, of K by H, loosely speaking, that by elements from H. Okay. And similarly the same holds if you change the direction, that is if you start with the right cosets of H and let K act on that, the similar observations you can make there as well. Okay. So yeah, I think I will just finish with one thing. We will just touch upon the actions by conjugations, and in the next lecture I will start from that. So let G be a group, G acts on G by conjugation. So for any A in G, the orbit is of the precisely of this form. Okay. This is going to be the orbit of A. We call it so in this case, when the action is by conjugation, we call it the conjugacy class of A, and denote this by CL. It's a temporary notation, CL of A in G. So it's the conjugacy class of A in G. Okay, what's the stabilizer? Stabilizer consists of precisely all these elements. Okay, and this has a name. This is called the centralizer of A in Z. Centralizer of A in G. So when G is finite, it's quite clear that from the orbit stabilizer theorem. Okay. So number of elements in the size of the conjugacy class is nothing but the index of the centralizer. Index of this centralizer. So in view of this, you can write down the class equation for this action. So like then G will be written as first the fixed point. So when G is finite, center of G together with entities of this form. So AIs, I from 1 up to K. So AIs are representatives from all from all non-trivial conjugacy classes. That is the conjugacy classes having size at least 2 non-trivial conjugacy classes. Okay, so you can write from the classification in this form, and I will finish with this observation that remember that centralizer of A consists of all elements which commute with A. Okay. Now, therefore, centralizer of any group, the centralizer of any element naturally contains the center, right? Naturally contains the center because centers commutes with all elements, and in fact, this also shows us that center is nothing but the intersection of all centralizers. Okay, center all centralizers. Yeah. Okay, so then the next lecture I will talk more about conjugacy action, and in fact I will be looking at the special situations of conjugacy actions when G is equal to Sn, A, I mean symmetric group, alternating group, and dihedral group. Okay, so enough for today. Okay, with that I finish my lecture.